So, on to solving exponentials in logarithmic equations. Now, last lesson, I made a comment when we went over the properties. And I said the number one property that we're going to use for logs when we solve equations is bring the exponent down. That when I take a log of something, that allows me to bring the exponents down. Logs are forever tied to exponents, okay? And this is a great situation of just that. So let me demonstrate here. We have the exponent is connected to this right here, isn't it? It's not connected to the 20, it's connected to the 1/2. Now, if that x was a coefficient, if it was just a number that was out in front being multiplied, that would be a lot easier to solve for than it just being right there in the exponent. So, that's what log is going to do for us. Now, before we take a log, I want to make sure that whatever I want to take a log of, whatever the exponent is directly connected to, I want to get that alone. Which means I want to get rid of my 20. If I'm multiplying by 20, I want to divide by 20, right? So if I divide this side by 20, this cancels. I divide this side by 20. Remember, basic rule of algebra. What I do to one side, I have to do to the other. So now we have the following. My 20 is gone. I now have my 1/2 raised to the x over 3 equals, well, I can reduce this to 1 over 4. Okay? Now I can use log to bring down my variable, which is in the exponent. So, if I take the log of this side, okay, that takes my exponent and brings it down. X over 3 times, and it ceases to become the exponent. It's no longer there. But just like when I divided by 20, I had to do the both sides to balance. Taking the log, that's like a math function. That's like squaring both sides. When I square one side, I gotta square the other. If I divide by 20, I gotta divide both sides by 20. If I take the log of one side, I have to take the log of the other side. Yeah. So I'm just going to rewrite this now. I've got x over 3 times the log of 1/2 equals the log of 1/4. Don't go crazy and start typing the log of 1/2 in the calculator, put the decimal there, and type the log of 1/4. I mean, you can, but then you're just going to be writing large decimals, because they typically go on for a long time. So don't type anything in the calculator until you get your x alone. Aren't you solving for x? Wait till you get x alone, then whatever's on the opposite side, put that in the calculator one shot. Okay? One shot. So, if I'm multiplying x over 3 by log of 1/2, how do I get rid of that log of 1/2? I divide x over 3 times log of 1/2. I divide that by log of 1/2, right? Yeah. So these cancel nice. What I do to one side, I have to do to the other. Log of 1/2, okay? Now, I can't just divide by log and keep my 1/2 there. Log of 1/2. It's like if I have a square root of, I don't know, it's called 7. Okay, I can't just get rid of the square root and keep the 7 unless I square both sides. Okay, the square root. If I have a square root of 7, like x plus the square root of 7 equals 10, I can't just subtract a square root sign, can I? I mean, that would be ridiculous. The same rules are here. I can't just divide by log, okay? It's a function. It needs a number to be, to work. Okay, just like log, it needs a value to work, okay? So when I divide by log of 1/2, not by 1/2. Not by log separately, but by both. Okay. Now I'm going to rewrite this again to keep it clean. And as you do these, you're not going to have to constantly rewrite things, but when you refer back to your notes, you're going to see a good example, I guess. We have x over 3 now equals the log of 1/4 over the log of 1/2. Now how do I get this to be a log? Well, you're close, you're very close. Instead of the reciprocal, if I'm dividing by 3, I multiply by 3, right? So if I multiply this whole thing by 3, it is the reciprocal of 1/3. I want to keep the x. It's 3. So If I multiply this by 3, I can multiply this whole side by 3, don't I? Yes. So now x, all by itself, equals this right here. And guess what we're going to do? Just like it is there. So why would you put those logs in earlier and carry them down and run? Just put it in one shot. I use your alpha y equals because that's going to help. Meaning, keep the fractions fractions. So I know as I turn on my calculator, I start with a parenthesis and a fraction, right? And in that fraction, there's a log on top of it. I hit log of another fraction. Now, those are, the top is 0.25, right? 1/4. The bottom is 1/2, it's 0.5. You can do that, but be careful. 1/3 isn't 0.3. It's 0.3. It goes on forever. So you would have to use 1/3. So I'm always getting the habit of continuing to use whatever fraction I have. So that's, yes, absolutely. And just like it's written there. And then here it's the log of 1/2, another fraction of y equals 1/2. You gotta come out here, close that. Now I gotta close this giant parenthesis for that whole fraction with the logs, times 3. What do you get? 6. And it is 6. It actually is 6. It's great. So x would equal 6. And that's it. I mean, that's it. So basically, you just use basic algebra to manipulate your equation. And you go for an answer. Now, let's check this. If our original equation, x was 6, right? What is 6 over 3? What is 6 divided by 3? That's 2, right? So now it's 20 times 1/2. Well, 2 is squared, should equal 5. What happens when I square 1/2? What's 1/2 times 1/2? Come on now, don't give up on me now. 1/4, isn't it? So what's 20 times 1/4? That's basically 20 over 4, right? What is that? 5. It works. It works. It works, absolutely. All right. Example 2. How should we solve this one? Any ideas? Those of you that did that homework last night, any ideas? How do you think we should solve this one here? Thank you. So if I have the log of x squared equals 2, I switched these, but question, what's my base? 10. If it's not written there, it's 10 all day long. Nice, my God. So, what we have here is, if I can drop the log, and I've got 10 squared equals x squared. By looking at that, what's my answer? What's x? It should be 10, right? 10 squared should be 10 squared, right? So x should equal 10. So just for poo-poos and giggles, let's solve this. What's 10 squared? 100. How do I get x alone? I take the square root. Very good. So 10 equals x, right? You're missing one thing. What happens when I take the square root? So the answer isn't just 10. Because think about it right here. If I square negative 10, will it give me positive 100? So right here, this can be a positive 10 or a negative 10. That'll be the same thing. Okay? Because we're squaring it. Okay? So there's a square involved, always be careful. Now, if this 2 were to shift up, that'd be looking different, but okay? Simple. So we got a situation where, hey, we use log to give the exponent, okay? And there's times where we don't have to. If they already give us log here, we can swap that, right? This first one, they didn't give us log. We get a variable as an exponent. That's why we used log to bring it down. Here, well, we didn't give us log. Let's just do the mahogany thing, switch it, and we're good to go. All right. This is just FYI. Okay? Now, the common logarithm has a base of 10. Meaning, like you guys just told me, if there's no number here, we assume it's a base 10. Now, natural logarithms a base of e. So, if log base e of 7 equals this whole decimal here, okay? Well, natural log has a base e. So technically, if there's no number there, it's a base e for natural log, okay? So if you have to log with a base e, that's just like saying natural log. Okay? Log base e is like natural log. But here's the huge thing to remember. This is nice. Okay, now I know log base e. That's not the critical thing to remember. The critical thing is, if there is an e in your equation you're solving, you need to use natural log. How come? Because natural log and e cancel each other out. Remember? That is the golden rule. So yes, this is good to understand, but if there's an e, you need to use natural log. Now, there have been students that I've taught in the past that when they have a problem with this first one, natural log and log have the same properties. They just use natural log instead of log. Instead of using log and then saying, oh, I've got a problem with an e, now I need to use natural log. Instead of trying to remember both, they just use natural log for everything. If it doesn't have an e, I would come up with the same answer. So instead of my answer here being log of 1/4, this would have been natural log of 1/4 over natural log, and you would have gotten the same answer, 6. So people are like, well, I'll just use natural log, and then that way I don't have to remember whether there's an e or not, I'm using natural log, so that covers it. Students do that, and that's fine. Okay? Yeah. So, the big thing I just said is that L and an E, they cancel each other out. And I will show you 2 examples, and you'll get it. It'll be a lot easier. So, ln and e cancel each other out. It doesn't matter if I have an e and I apply an ln, or if I have an ln and I apply an e. Doesn't matter, they both work. For example, I have e here. Oh, there's an exponent that's a variable. I want to bring it down. I'm going to use logs. I mean, I can use a log of both sides, but then it's going to be like that first one with a fraction, it's going to be crazy. Or, because there's an e, I'm going to take the ln of both sides. So what happens on the left side? Yeah, the ln and e cancel. I just have 2x equals the natural log of 14. I mean, if I were to use regular log, and I could, I'd have a log on both sides, and I'd have to divide log by the log. I mean, it would just be a bigger problem to do. It would still be doable, but it wouldn't be as easy. So what do I do with the x alone here? I just divide by 2. So x equals, and you put this in the calculator just like that. Now, give that to me 3 decimal places. And if I'm going to have to round, I don't want to say it's equal, I say it's approximately. What is the ln of 14 divided by 2? Is it 320 if I round? 320 if I round. It is 1.31916, something or another. Now, let's check that, okay? In our calculator, if I say alpha y equals, because I use that fraction, and I say the ln of 14 over 2. I enter, there it is. That rounds to 1.320 if I go to the thousands place. Now, if I want to check that, I don't want to check 1.320. I want to check that whole number. I'm going to store that into x. Remember our store button? Store. Up beyond. It's going to take my answer and store it into x. There you go. So whenever I hit x, that big long number is in there. So let me check with our original problem right here. If I put 1.319528665 into my x in the exponent, should I get 14? I should. Above the ln in blue is my e. Okay, so I hit second. And I want to make that to the 2x. That should be 14, right? There it is. And it is. Yeah, it's great when it works out. I can't tell you it's wrong if this happens. That's the beauty of math. Now, we use ln when we had an e. Let's do the second problem. We have ln and we can use an e. But be careful, because when I use an e here, I make it my base, and this becomes my exponents. So if I make e my base here, I need to make my e the base on the other side. Okay? And how does that work? Well, if I have 5 to the third, doesn't that equal 5 to the third? If the bases are the same, the exponents have to be the same for them to be equal. So if these bases are the same, the exponents still have to be equal, so it still works. And now here's the beautiful part. What happens to e and ln? So guess what? X equals e to the third. Someone put e to the third in there for me. Get a calculator. And round that 3 decimal places. So x equals, what do we got? Well, give me 3 decimal places. Okay, 20.085. Let's check that. All right? We have e to the third. 20.0826. You know what else is 6? Bam, that's fine. Because if I check this, if I want to put it in the original equation right here, right? Well, I'm going to put this value in for my x. I'll store this in the x to check it. Okay, so that's my x. So the ln of x should equal 3. I mean, there you go. There you go. There you go. So, modeling logarithmic and exponential equations. So a lot of times I get, are there many other real world problems? When am I going to use this? And some of the times the models, real world models are, irrelevant to you guys. You don't care. And some of them are pretty cool or important. This one's pretty cool or important. Earthquake, not quake. There should be an R there. Earthquake intensities, the Richter scale. You hear here in the news somewhere in California, they have like a 3.8 earthquake, and the aftershocks are 2.50. That's actually, they got to use exponentials for that. Okay, as you know, earthquakes can be devastating. It's nuts. Chemistry, they measure acidity of solutions, like pH values. That's a health concern, right? You want some acidity, you don't want too much. You can get too much things with acidity, like juice in it, certain juice, like apple juice, very acidic. That will digest the stuff in your stomach for you, and it becomes like when you use the restroom, and you're passing solids. It's all you're passing liquids. It's very unpleasant. So
you want the number to be closer to like I think it's 7.
Are you talking pH?
Yeah.
There you go. So what happens if you get more and more and more? Then it's just like it's more acidic, which is dissolving more your solids, and I wouldn't advise. Drink juice is healthy, just like everything in moderation. Here we go. In my class, when I teach PreCalculus in Algebra 2, I always set, remember the dead body with the rope, the police tape, whatever? Everybody's always like, when do we do that? This is what we do for this stuff right here. So that will be coming up soon, that project. Okay? Newton's law of cooling. Newton, among a couple other people, were responsible for creating calculus, and he also came up with this. Okay? An object that has been heated will cool to the temperature of its medium or environment that it has been placed in, okay, which is the surrounding air or water. An environment doesn't have to be in a room like this with air, it can be underwater or whatever. Now, the temperature T of that object at any time little t can be modeled by Newton's law of cooling. Right? And let me explain to you what each one of these things mean. I buy a cup of coffee in the morning on the way in. Anywhere from 150 to 200 degrees, depending on who makes it. I put it in this room, which is 68 degrees. That coffee, I let it sit long enough, will cool down to just about 68 degrees. It won't get colder. This room isn't cold. I mean, if I added an ice cube to it, it might get colder. But over time, it will get as cool as the medium. I take a hot piece of steel. What's that? Yeah, That's it. You hear the drink, it's going to become room temperature. Oh, we need soup. That's great. It's so cold outside. Oh, it's room temperature. Let me heat it up. You know? People, you ever see those guys make swords and they put metal and it gets really hot and then what do they do to cool it? They throw it right in water, right? Yeah. Water's the environment. Depends on what the temperature of the water is or to cool the metal. So, with that said, let's take a look at this. Now, you're going to be given 2 or 3 temperatures, right? This first one, capital T sub little t, that is your final temperature. Now, I want you to write something else besides final temp. This is called what? Newton's law of cooling. So this will end up equaling your cooler temperature. Your cooler temp. Okay, like if I had coffee and I put it there and it came in to 200 and it cools to 68, this is the 68. Okay? I have a lot of students who say, oh, well, if the coffee is, okay, there's 200 degrees and 68 degrees, it must equal 200 because that's a bigger number. No, this is Newton's law of cooling. It should be the cooler number. Okay? T sub 0, well, everything always starts at 0, doesn't it? So that's your starting temperature, your beginning temperature. And if you're given 2 temperatures, that is typically your hotter temp. Okay? Coffee's 200, it cools to 70, guess what? T sub 0 is a 200. T sub t is your T of t is your 70. Now Tm, that's just the temperature of your room or your medium of your environment. And note that in our equation, it happens twice. So if the room's 68 degrees, I put a 68 here. And I'll also put a 68 here. Pops up twice. Okay? T, well, that's just time. How many minutes does it take to cool? How many hours does something take to cool? Whatever they give you, that's your time variable. Now, I'm going to skip down to E right here. As you know, E is a number. It is not a variable. You do not have to solve for it. There's actually the E in your calculator. That's what you plug in. You want to be precise. You don't want to round to 2.718. You put that E in there and it will calculate the whole number. Last but not least, we have another variable that's K. This is sometimes, it's dependent, and I put on properties, really it's dependent on the situation. Which is basically saying you have the properties of the environment, properties of your situation. What's happening? Meaning, K will be different if I have coffee cooling in this room than if I have metal cooling in water. It's a different environment altogether. Okay? It's a different situation. Typically, there are some problems where they say, okay, solve for this, here's your K value. Sometimes they give it to you. But typically in PreCalc, we have to take our environment, solve for K first. Once we have that, then I can solve for K in the future. Meaning, they will give us a problem like this. They will say, a hard-boiled egg at temperature 96 degrees Celsius is placed in 16 degrees Celsius water to cool. 4 minutes later, the temperature of the egg has cooled to 45 degrees. Right here, in these first 2 sentences, they give us a starting temperature, an ending temperature, a medium temperature, and a time. We can find K based on that. Okay? Now, once I have K based on this situation, the egg starts at 96, at 16 degree water, I can use that K for any time in the situation, because it's constant for this specific situation. Meaning, once I know what that K is, now I can find out, well, if it started at 96 and it goes to 20 degrees, I have my K. Now I can find that time, because the K doesn't change. That K that we find will not be the same if I was using coffee in this room, metal in the water. You see what I'm saying? It's different. So really, we use this twice to solve the problem. Okay? And once we get that K value, then we can figure out, well, what happens, how long does it take to the 20 degrees? And let me show you. I'm going to do this. I'm going to clone this. Put one over here. Put one over here. Split that down the middle. And we'll stop it to this problem. Okay? Now, hard-boiled egg is at what? Which variable do you think that is?
That's the initial.
Yeah, that's what it starts at. This is my t sub 0. So right now this is 96, t sub 0. Minus some value, it's e, which is a number, so that won't change, and k and t will. Okay. It is placed in 16-degree water to cool. What is that? The 16, yeah, that's the environment. That's the water. It's being put in the water. So the egg is now in the water. That's the environment and its surrounding. That goes in two places, right? That goes here. See, so that, and then that goes here in front of this plus sign. So we're not multiplying it as plus. Okay. 4 minutes later, the temperature of the egg has cooled to 45 degrees. Now, if I need to solve for k initially, that means I have two more variables. This little t and this t of t. In that last sentence, can you figure out which is which? Well, the second sentence. Yeah, 4 is the time. This is our time. And then what else is, what I got?
145 feet.
Yeah, it's T of T. That's your ending temperature. Remember, I have the egg at 96 and it's 45. It should equal the cooling temperature. It's Newton's law of cooling, right? 45. I compare this to the Pythagorean theorem. And you're looking at this right now and you're like, Visca, no way. I'm going to explain to you how I compare it to the Pythagorean theorem. Pythagorean theorem. Okay, now, when you first learned the Pythagorean theorem, you're like, oh, okay, it's weird. But you did it. And you did it. And you did it, and you did it, and you did it, and you did it, and you did it. And even your parents, or your relatives, or your cousins, whomever, that are not good at math, know that a squared plus b squared is c squared. Because you've done it. Once you do this once, it's the same process over and over and over again. Watch. The math is not that difficult at all. All right? And when I say not difficult, what is this? What is 96 minus 16?
70.
That almost 80.
Yeah.
I multiply that times my e to the negative. Well, negative k times 4. Let's call it negative 4k. I'll write that with a number first. All right. Now I also got to get my 16 over, right? What is 45 minus 16? 29? Good. Now, this is gone, right? That's the first step. You bring this number over, the 16 in our case, and you combine. Nothing different. Look at this, we just need a log to solve for k. We just did that, right? Is there a variable in the exponent? So we got to bring that down using log. Now, which log do you think we're going to use, log or natural log?
Natural log.
Yeah, there's an e there. Natural log. It's going to be easy. But before we do that, don't we want to take the natural log of just this? So we want to get rid of the 80, don't we? So let's divide this side by 80. Boom. Divide this side by 80. I was thinking subtraction. So this goes away. We have e to the negative 4k equals, guess what? We can leave that as a fraction. You don't have to type that in with log. Don't try and solve it. Leave it. I mean, if you're one of these people who say, well, I have to reduce it, right? I mean, fine, go nuts. If it's 1 over 2, you want to say 0.5, that's great, good for you. But why have to do extra work when you know the calc's going to do it for you? Now, what do? I have to do the natural log. I said, how we solve for a k? So if I take the natural log of this side, I have to take the natural log of this side, right? And doesn't my natural log and e cancel?
Yep.
So right now, right in front of us, we have the natural, and I'm rewriting a lot of this stuff so you can see the steps in your work when you want to look back at it. But as you get good with this, you're going to realize, you really can not write as much as I can. E equals negative 4k. What's the last step to get k alone? Divide by negative 4. Divide by negative 4. Divide by negative 4. So let's put this in our calculator, and that's what k is going to equal. So k, and give it to me 4 decimal places.
Negative 1, 0,
Let's see. Let's see. I hear one. You guys work it out. I'll work it out up here. You tell me what you get. See if it's the same thing.
Oh, I know, I forgot to divide it by 4.
Okay. -4. Don't forget. Sounds about right. Outline of 29 over 80, right? All divided by -4. That's what it is. 0.25. And I'm going to show you something. Hopefully that's still in your calculator, okay? For one reason. That is approximately 0.2537, right? If I round, that goes up to a 7. Now, I don't want to round until I find the minutes, because they're asking how long it's take to get to 20 degrees, right? If I cut off all this and make this a 7, that's going to slightly affect. Because now this part is not in my exponent anymore, is it? If I cut it off like a minute. So what I'm going to do is I'm going to store that. So I'm going to take, and you know the beautiful part is, there's actually a K above the 8, the parenthesis. If I hit alpha, parenthesis, that's my K. So I'm going to take my answer, hit the store, and I want that right in K. Look at that. So now when I solve the problem, I got to put a K in there. I just put in K. That whole big long decibel's in there. So now that we know what K is, we say our K is approximately 0.2537, but we'll use the one at the calculator. It's just for us. What is our starting temperature? It still started at 96, didn't it? It started at 96. Okay? The room temperature is still, or the water temperature, is still 16, right? So that goes here and here. What's our final temperature this time? They want to figure out when it hits this. Now that I have K, I can solve that. Because now I'm finding T. If I need to find T, that means I should have a number for K. I can't have two variables to figure what they are. Alright? So when it gets to 20, and now that's E, now I got to negate K, right? Negative 0.2537. Of course, in our calculator, when we type this in, we're going to use that big number in the K. Alright? Or maybe the problem says find K and round to 4 decimal places, then use it. If that's the case, you do that. If they don't say that, store that number. You want to write it all out, then type it all in, go nuts. Okay? So now, before we get going on this, what did we really do on the left-hand side? I subtracted twice, right? I subtracted this for 80. I subtracted this to get 29. I divided once. And then I apply my natural log. And then for poops and giggles, I just got to get rid of that -4 and divide again. So subtract, divide. Natural log divide. I mean, literally, you know how to subtract? Good. Well, heck, you should. You know how to divide? Fantastic. Natural log is K. That's what you know. A squared plus B squared is C squared. A squared plus B squared is C. A squared. Go. Subtract. Divide. Natural log. Divide. Subtract. Same thing here. Subtract. Divide. Natural log. Divide. So let's do it. You tell me. What is this? Still 80. Okay. What do I do? And I still have my E. Oh, let's not forget. We got to solve for that T, don't we? Negative 0.2537T. What do I do? What else do I do? What is 20 minus 16? This is gone. I subtract, then I do what now? Divide. Same process. Divide by 80. You can leave this 80 over 4, or you can leave it, change to 1 over 20 because it reduces, but I don't know, it's up to you. I'll leave it 4 over 80 equals E to the negative 0.2537T. Alright? Natural log. I mean, cut this to get out of the way. Natural log, so I take the natural log of this side and the natural log of this side. The natural log of 4 over 80 equals what? They cancel. That's the last step. Yeah, I got my time. It's the same thing over and over. I mean, every once in a while, maybe they Oh, okay, do you want to solve for the initial temperature, whatever? I don't know. I really haven't seen too much of that. So, tell me what you guys get. And what do they want the answer in? Now, keep in mind, when you get here in the calculator, you're going to divide by negative k, right? You're not going to divide by negative 0.2537. You want to put that k in there for an exact value. Then what's the nearest minute? What do they say? Usually let's find out when the just how many minutes. I guess we'll round to the nearest minute. Or, tell you what, we get 1/10 of a minute. Anyone get an answer?
I got 11.808.
Let's see if you're right. Bam! We have the natural log of 4/80, right? You could say 1/20, that's fine. Divided by negative k. No, make sure your k is negative. Remember, it's negative k. Okay, divided by negative, and I'm going to put my k right there. 11.80. Almost approximately 12 minutes, right? There you go. And we use our regular k, so that's approximately, t is approximately 12 minutes. I mean, shouldn't that make sense? If I look at my problem, it took 4 minutes to get to 45 degrees. It shouldn't take 3 minutes to get to 20 degrees. It's going to take more time to cool longer, won't it? It should. So, I mean, 12 minutes, that's good. Good guys. We'll continue these notes when we come back in the 3 days weekend. All right, guys? No homework. If you open anything, get it done.